Hey, what's up, guys? This is Chung here. So today, let's take a look at LeetCode problem number 269, Alien Dictionary. So this one is a very classic uh, problem. So basically, there's a new alien language that also uses English letters, but the others among those 26 letters are unknown. So all we have is like a alien's words dictionary, right? Given by this kind of given by this in this format, and each word is sorted uh, uh, lexicographically by the rules of the new language, and I'd ask you to return the letters of the order of the letters, right? That appears in all of the words, right? Based on this new alien language. Right? For example, we have like this word, we have 5 words here, right? And the output is this one, WERTY, because W has to come before E and so on and so forth. And if the given input is invalid, return none, basically return empty. And if there are multiple valid solutions, return any of them. Okay. So what does this mean, right? So we're given like this word, so which means that the first word is smaller than the second one, right? And the second one is smaller than the third, so on and so forth. So for example, let's comparing the first one, this one, the first one, second one. You know, since WR are the same, so the first difference is T and F. So which means that T needs to be smaller than F. So that's the first one, right? And since everything after all the words after this current word is going to be greater than this one, so which means that we have to for the current one we have to loop through all the remaining words. Then the second one is we have to loop through this. We have to compare WRT and the ER, right? So the first letter is different, so which means that W equals to needs to smaller than the E. So for this one, same thing, right? So it's also E, and for this one, W will be smaller than R, and that's how we get by choosing the first word as and then comparing with the remaining ones, and this is the relationships we have here, and then we do the second one, right, and then third one, so on and so forth, until we have looped through all the combinations of the words, and then we can have like a relationships for between 2 letters. And so what is this? This is actually a graph, right? It means that if t is smaller than f, then it means that we have to go through t first, and then we can go to f. Similarly for W and E. So for W, basically we have to go from W first, and then we go to E. So similar from this R here. So with this kind of like ladder relationships, actually we can build like a graph. Okay, and after that, it's like a very classic topological sortings, right? And we can use integrate dictionary to help us to sort, to find a valid a valid orders, right? Of all these letters. Basically, we start from the letters whose integrate 0, right? And every time when we process the current letters, for example W here, we're going to remove the edges, right, for all its neighbors, which means that the integrate for E will be minus the subtract by 1. The integrate for R will also needs to be subtract for 1, right? And then if we have a new letter whose integrate becomes to 0, it means that okay, so now it's time to process this one, then we can just add it to the queue. And in the end, and there's like this some invalid cases, right? For example, this example 3 here, we have basically this is like a circle, right? So we have Z pointing to X, and then we have X pointing to Z. Obviously, this is a circle, which is invalid case. So the way we're checking if there's a valid in the end is that we simply check if the length if the length of the answer is equal to the same, the total letters, right? Total letters. If they're not the same, it means that we have find a circle, right? And then we can simply return the empty string. Cool. So, but there is like a little tricky another invalid scenario, which is the when we're comparing this kind of words here, there's another invalid case. Basically, if we have A, B, C, and then A, B. So it didn't tell you in these examples here, but there is like this case in the test case. So for this one, right? As you can see, right? So the AB and AB are the same, but the length of this one of the first one is greater than the second one. So in this case, actually, so it definitely, since the AB and AB are the same, so the second word has to be smaller than the first one. But that's why it's invalid, right? So which means that we also need to consider this edge case when we build our graph. Cool. So let's try to build our graph then. The coding will be it's going to be a little bit long here, so I'll try to code this as fast as I can. So we have integrate, right? So we're default dictionary of int, right? So that's an int, and then we have a graph. Graph is going to be the default dictionary. I'm going to use set here, okay? And then for the letters, I'm just using a letter set to store all the letters. And then we have a n length equals to the words, okay? So so for me, I just use another for loop here just to populate the letters. Basically letters dot add c. So I'm just using this one to populate the letters. I think you can also maybe integrate this part into another for loop, but I'm just doing this in this way. You can choose another way. And then let's try to build our graph and integrate, right? So basically, we need to compare these two words, right? So the i's from 0 to n minus 2, since we're going to compare with the next word. That's why, and then the second word starts from I plus 1 and then to n, right? Then we have word 1 equals to words I, and then word 2 equals to words j, right? So those are the two words, and now we need to find the first letter, right? That is who is different, and then that's going to be the edge, right, for us to build. So I use this way, okay, word 1 and length 2 equals to length of the word 2, and then I'm going to have a pointers, so p2 equals to 0. So basically, while p1 is smaller than n1 and p2 is smaller than n2, right? So we have a current letter 1, word 1 p1, and then c2 equals to word 2 dot p2, right? So if c1 is equal to c2, right, then we simply continue. And then with p1 plus, right, and then p2 plus 1. Else, right, else we find the first two letters who are different, right, and then we can do this, right? So graph dot c1, right, add c2. Basically, we're building like a edge from c1 pointing to c2, and then we do integrate of c2, right, plus 1, okay, and then we can simply break. But there is like a little thing we need to be careful. as you guys can see, since we're comparing the different words, it could possible that we have seen C1, C2 multiple times, right? If that's the case, right? If that's the case, the graph C1, C2 is fine because we're using a set here, but the integrate of the C2 might be duplicated, right? If we see W and R twice from two different words, right? And then this integrate of the R instead of two, instead of one, it'll become to two, right? That's why we have to do a check here. Basically, if C2 are not in the graph of C1, then we can just add the edge and then also increase the integrate, right? So that's that. But okay, but one more thing, right? We also need to cover this A, B, C, and AB case, right? So how can we cover this case? I mean, there are different ways. So the way I do it is that, so for this one, so what's going to happen? So we didn't find like a match. We didn't find a difference, right? But the second one is the length of second one is smaller than the first one. That's our condition, right? So that's why I'm going to create like a find diff flag here. So at the beginning, it's going to be a false, right? So if we ever find like a difference, right, we can just set that one, find difference equals to true, right? And then in the end, we do a simple check here. So if not find difference, right, and the n2 is smaller than n1, then we simply return the empty string, right? So that's how we build the graph and our integrate dictionary. And then now we can just do topological sortings, right? Topology sorting now. So we have a queue, right? So this is like more like a template. I use a DQ basically, So so we have letters, 4 letters in the letters, right? If C not in integrate, right? That's how we initialize this DQ here. Basically, as if these letters are not in this integrate, means that it has like 0. It has 0 integrate, right? Okay. So, cool. So, and we have our answer equals to this one, and then we just do like the topological sortings, right? So we have current equals to q dot pop left, right? And then we add this one to the answer, and for the neighbors in graph dot current, right? And then first we decrease the integrate by 1, right? And then if the integrate of neighbors equals to 0, right? And then we can just add it to the queue so that can be processed later on, right? And yeah, and then in the end, once this while loop is finished, right? So it means that we can simply return the answer, but we also need to check if there's a circle, right? So the way we check the circle is we just compare the length. If the length of the answers equals to the length of the letters, right? Then we just return answer, else empty. Yeah. So yeah, I think that's it, right? Yeah, if I run the code. Oh, I call it letter set, I think. Yeah. Okay. Yeah, so that's it, right? So for the time space complexity, right? I mean, So here we have like the we have n square, right? So this is n square of the length of the word, right? And then we have like also have like a word for each of that, right? So maybe at times like another one. Since the length of the word is also 100, so I'm assuming this is n and this is n. So we have another n here, right? So to build the dictionary and integrate, we have n cube, right? Time complexity. And for the topological sortings, it's just so the ladder here, that's the n ladders, right? We have in total, we have, oh, actually it's only 26 because the, we only have up to 26 letters, right? So for each letters, we'll have like up to 26 uh, up to 26 neighbors, right? So that's why, for this part, actually, it's like more like a constant, right? 26 times 26. Yeah, something like that. Yeah, because for each of that, we're gonna do a neighbors here, right? And then, yeah. Yeah, so, I mean, even the 26 letter is not 26 letters, it's more than that, since, so for this part, since the number of, since we're doing like a BFS, or like we're doing a traverse, right? So the total time complexity the last part, it's going to be all of uh, vertices plus the edges, right? And the edges, right? The edge is going to be the number of the length, right? Because for each of uh, the n is like the length of the words, right? Because between two words, right, we're gonna only have generate one edge. Yeah. So that's why in the end, I know for the second part it's gonna be a little bit complicated to calculate, but in the end, the time complexity for this one is gonna be a n cube, which is the basically the total letters in all this kind of words. Yeah. So I guess that's pretty much it is. I'll just stop here. And this is very, I think it's a very classic topological sorting problem with a little bit edge cases when we try to build this kind of graph and integrate dictionaries. For example, this kind of this edge case, right, where the second word will be definitely smaller than the first one. Then we simply return an empty string. Right. And other than that, another one is that we have to be careful that since all the letters behind after the current letters are all greater than it, so which means that we have to compare the current one with each of the one who is after that, who comes after the current word, so that we can complete our uh, uh, graph. And also when we build this integrate here, uh, to make sure we're not double counting the integrates for the same edge, right? We need to check if this edge has already been added before or not. Yeah, other than that, I think that's pretty much it is. Cool. Thank you so much for watching this video, guys. Stay tuned. See you guys soon. Bye bye.